Good morning, everyone. Thank you for joining us today on our tech talk on our FRP Rebar offering. I'm just going to allow a minute or so for people who are en route to join us, and then we can just start this up. Hi, everyone. I think we've got uh, people who wanted to join, so I'm just going to start the proceeding for today. Hi, I'll just give you a brief introduction of myself and the guest speakers that we have with us. I'm Rasneesh. I work with Treadwell in the capacity of project sales manager. I look nationally into the industrial segment and new products. With us, we have our tech partners from SFT Canada, who have plethora of experience and expertise in specific to FRP rebars. I would allow Tawfiq and Ahmed to say hello to everyone, and then we can start with the presentation and then later on do a Q&A session.
Hi, everyone. Thank you for attending. Look forward to your questions later.
Hello, everyone. Thanks for attending. Nice to meet you. Yeah.
Hello, everyone. Just as a means of introduction, just like any other composite FRP product, we leverage the intrinsic properties to solve for a problem. And the case in question here is corrosion and the cost of it. As per CSIRO, annually, it costs us about 3.5 to 5% of our annual GDP in Australia due to corrosion and its estimated damage. It's not just limited or an isolated trend that we see here, but even in New Zealand. Perhaps it is imminent that we address it. And by means of FRP, we intend to offer a part of the solution. Essentially, as most of you would be experienced with FRP, we do not intend to replace all the steel in the world, but mutually coexist based on application and problem to solve for, which can be in form of corrosion, accessibility, conductivity issues, so on and so forth. Perhaps to give you a short introduction on how FRP rebars are made. They are made through a process called pultrusion. And in terms of the raw material, there are two typical raw materials, which is the reinforcement in form of glass rovings, which are helically wound, and the matrix is either an epoxy or a vinyl ester resin. These are helically wound and are impregnated into the resin of choice, depending on the application, and perhaps are heated to a curing temperature, after which they can be cut to length. This process is continuous and hence is suited for voluminous runs. And just to give you an update on different types of reinforcement that are possible through this process, we can use glass, we can use carbon, we can use aramid and basalt. And so are the resin choices, which are vinyl ester and epoxy. In specific to us currently, where we stand, we are only offering glass as the reinforcement, and most of our products are based using epoxy resins. Now, some benefits of rebars, they, as similar to other FRP products, they are non-corrosive, perhaps solve for harsher chemical environments where the conventional material have a lower design life and have to be cared for in terms of refurbishment costs. Perhaps have a longer design life, which is over 80 years. They have greater tensile strength, almost 3 times than the conventional steel, which is of the tune a 1000 MPa compared to a 420 MPa to steel. They also offer a better bond strength to concrete, which is from 18 MPa to 20 MPa compared to conventional 10 MPa of steel, and are 5 times lighter than steel. They are also electrically and magnetically neutral. So that means one does not have to account for additional cost of bonding and earthing to avoid slip and touch potential. Nowadays, as we see with the global trends that we are becoming more and more sustainability conscious, perhaps both upstream and downstream producing glass fiber reinforced rebars is less energy consuming. Hence, the carbon footprint is 35 to 45% estimated lesser compared to the conventional choices of rebars that we have currently in steel. In terms of a product offering of rebars, we are having two different variants of rebars. One is the base offering, which has a modulus of elasticity of 45 GPa and over. These rebars are used mainly for non-structural purposes. However, there is a premium offering which has a larger modulus, which is 60 GPa and over. These can be used for structural and load-bearing purposes. A little more in terms of the advantages, as we were discussing earlier, the design life estimated by using these products is 80 to 100 years. Significantly low energy consumption, both upstream, downstream. There is no thermal bridging that is required. Because of the lightweight nature, the carbon footprint is lower in terms of logistics as well. In some cases, depending on the application, one can also save the concrete cover, because since it does not corrode, we can avoid accounting for larger crack propagation by having reduction in the concrete. But again, there are certain variables to be considered. There are cases where off the shelf, if one is comparing the material price itself, there are certain sizes where FRP might tend to be slightly expensive compared to the conventional material. However, when one compares the end-to-end cost, which is cost of the material, installation cost, logistic cost, it has been seen that overall project cost gives one a 25% to 30% saving in most of the cases. Would like to touch base on certain FRP rebar standards. In Australia, currently, we do not have a design standard. However, there are established international codes such as ACI 440, AASHTO, LRFT, and Canadian standards such as CSA 8608, C86806, which offer key guidelines for structural engineers to design with FRP rebars. These can be used to design and construct structures ranging from building to bridges. In terms of progress, I think Queensland is leading the way with acceptability, where there are certain technical standards that have been coming out, such as AS 5204, where GFRP reinforcement has become a standard for concrete deck pontoons, floating walkways, planks, and transition slabs. There is a discussion on design standards that probably are expected to come out in future, but the timelines on it is slightly uncertain at this point in time. So the globally accepted standards are a go-to guide for most of the engineers currently. Apart from the AS 5204, we also have MRTS 271, MRTS 301. These are technical and acceptability standards. They do not include or inculcate the design aspect of things. In terms of the product availability or the offerings that we do, we have the standard stocks length of structural and non-structural rebars, which have varied diameter ranging from 2 mm and up to 51 mm. So size or diameter is never a problem. They can be used as rock bolts. And in terms of ancillary or accessory products, we also offer bench, stirrup, share legs, so on and so forth. There is also a product offering that we are working on, which probably would be a replacement or an alternate for SL62 and SL82. The application where these products can be used are bridges, tunnel segments, barrier walls, diaphragm walls, wharfs, substation, garages, pavement, fence systems, so on and so forth. Some case studies which probably would give you an insight on the acceptability of this product in Australia. This is fairly a new product, and in terms of acceptability, I would say it is still an uphill task right now. However, globally, because of the availability of design standards, they are much widely accepted. However, there have been a couple of marquee projects where these have been used, such as Point Wilson, Frankston Dandenong Road, Horn Island, and Westgate Tunnel project. And very recently, these also have been specified in the South Australian Torrens to Darlington project. Would like Tawfiq and Ahmed to touch base and talk about a couple of international projects where their products have been used. Ahmed, if very briefly you could, just introduce the application and talk a little bit.
Hello again. Thank you, Rajneesh, for this opportunity to introduce and discuss our information about GFRP bars and their applications. As we can see, one of the most beneficial and efficient applications of GFRP reinforcement is slabbing on grade construction. Since, as we know, that this type of reinforcement is mainly used to that control due to shrinkage and temperature changes rather than for flexural strength. So we don't need reinforcement for flexural strength or any strength. We need only the reinforcement to crack behavior and the crack due to shrinkage and temperature changes. The high tensile strength and non-corrosive nature of GFRP bars make them an ideal solution for this type of application. We already used SFTec GFRP reinforcement in factory with 22,000 square feet factory in Quebec in Canada. Another crucial application of GFRP reinforcement concrete in bridge deck slabs. As we know, or you need, I can explain this. The most beneficial application for GFRP reinforcement for also bridge deck slabs. In Vermont, in USA, a single bridge was a total length of 43 meter and width of 12 meter. The deck slabs was was fully reinforced with GFRP bars in USA. GFRP reinforcement are also significantly integrated in pavement construction. Because one of the solutions to preventing to preventing the corrosion of steel reinforcement and limiting concrete cracking in pavement to replacing the steel bars with GFRP bars. These projects in Quebec presents a long-term field study on a busy highway in city of Montreal, which is known to receive a heavy snowfalls. The field test run for 30 months, followed by visual inspections every 6 months, performance assessment, and using number 5 GFRP bars. Another application, we can use GFRP bars or we can consider GFRP bars the first choice in tunnels and infrastructure applications due to the superior durability and corrosive resistance. This characteristic make them particularly suitable for harsh environmental conditions and the best choice to replace the traditional steel reinforcement with GFRP bars. In particular, tunnel lining segments and soft eyes for tunnel boring machine. All of this we can use easily GFRP bars for infrastructure projects. Also, we have some projects around the world from United Arab Emirates. Also, we have the Gizanic channel projects. It's the channel will expose to the channel when we completed. It will the world's largest project to be constructed using GFRP bars. You can imagine we use 23 kilometer the long mitigation channel. All of this channel reinforced with GFRP bars.
Thank you, Ahmad. That was a good download and touch base on the use case. And I think that would have given our audience a good insight on the product offering. I think I'll open the floor for any questions that might be there and we can together answer them. So Emma, there's one question on the limitations of FRP use case where it is usable and not usable. Would you like to take that?
For GFRP parts, we need at first we need to talk about if we use the GFRP parts for structural element or non-structural elements. For non-structural elements, we can use GFRP bars for all non-structural elements, but for structural elements, we need to take into our consideration the stiffness of our GFRP bars when we design when we involve the bars for slabs for walls, because you know that the main problem of GFRP bars is the stiffness compared to steel, but all GFRP codes and standards addressed the solution of this issue and provide design equations to can check everything about the serviceability to meet the requirements of serviceability and strength requirements.
Thank you. And can they be used in concrete beams?
Yes, you can use GFRP parts for all applications, for beams, for columns, for walls, for diaphragms, for slabs, for anything, for any types of loading, flexural, compression, combined loading, anything about tension only, any types of string action. GFRP parts we can introduce it and design these elements with GFRP parts for all elements.
Are there any special considerations required when using FRP reinforcement that you wouldn't do with steel reinforcement?
Or you mean by special consideration we need to consider?
Yes.
As I speak, as I mentioned before, the main not issue, but the main thing we need to address when we design with FRP bars, the stiffness of GFRP bars, because you know the GFRP bars have modulus of elasticity of 60 gigapascal, and you know that the steel bars to 200 gigapascal. So you see the difference, but this difference we need to consider when we design for serviceability. You know, if we, as an example, if we have two slabs and the two slabs with the same reinforcement, the GFRP bars, the moment resistance of GFRP bars 3 times or 4 times higher than steel bars. But if I have any project and need to convert the project from steel to GFRP bars, I just replace one by one from steel to GFRP bars. But the main consideration for me for serviceability due to the lower stiffness of GFRP bars. I need to check deflection, I need to check crack width. If those is okay, for me, all design I have will meet the requirements.
Thank you. Just wanted to touch base on one typical question that is asked on the ancillary or accessory parts. The bends can be done, but it cannot be done at site. If we get the drawings and the specification of it, we can do it at our own manufacturing and can be supplied there.
Yeah, we know that we need, if we need to make the bent bars for GFRP bars, we need to make order before with shop drawings to can produce with the required bent for this chips. But I need to add something. Nowadays, we already tested new resin of thermoplastic resin. You know that I need to add some information about that. The common GFRP bars is already produced with thermosetting resin. Thermosetting resin means when you produce the bars You cannot bend the bars or change the shape of the bars. But nowadays, all GFRP companies, especially SFTec, working on this type of resin is called the thermoplastic bars. This types of resin we will be make a capability to can bend the bars side.
But that's still a work in progress, right? The thermoplastic bars. So
Yeah, yeah, but we have already at our university we have already published more papers on this type of reason also. But it
I
will
see.
be involved for in the market very soon. Yeah.
And the ligages, if we are talking about beams, right? The ligages can be FRP as well.
Yes.
Perfect.
Maybe a couple of words. As a matter of principle, anywhere you put steel, you can put FRP. Okay. You just need to follow the other code, which is the JFRP related code. So follow a new code. The math is different, but you can use it anywhere you use typically steel. By doing so, you will save lots of time. You will need less people for installation because it's much less heavy. You will save lots of money in maintenance cost because there is no corrosion related to like you would have in the steel. The work on site will be safer. You will have less fatigue on site and therefore less accidents also. And your site delivery, you will finish the work. You can build a lot more and finish the work quickly and move to other projects quicker. Major improvements, basically. We SFTec, we offer our partners, basically Treadwell, engineering support to help them offer their clients conversion, meaning if you design with the steel, we help you convert the steel to FRP design so you can use it in build. Our SFT bar can be used in non-structural and in structural elements. It's been used in buildings up to 12-story high. Our bars are certified and tested in the two top universities that deal in composite rebar, Miami, Florida in the US, and Sherbrooke, Quebec in Canada. They are certified by ICC, which is recognized in Australia. The certification is ESR 5081. It's referenced on our website if you want to have a look at it. Thank you.
Also, Tawfiq, just wanted to add a little bit of context on that. For non-structural purposes, it's fairly simple as a rule of thumb. I think it's an apple-to-apple replacement in terms of diameter as well as the number of bars, right? And I think even at site, while installing them, one does not have to reinvent the wheel with the principle of installation, mostly. And what we've seen in the last couple of years, especially after post-COVID, steel has been much more prone to volatility in terms of supply chain as well as pricing, while FRP has not been so volatile in pricing. So if you're looking for a project which involves a longer time of completion, the volatility risks are much lesser. So I just thought I'll add that up as one of the closing statements. However, there are two questions. One can it be used in post-tension slabs?
For post-tension slabs, we cannot use GFRP bars, but we can use carbon or armate FRP bars.
Right. And how much effort is required to bend FRP bend bars into ligatures?
As I mentioned, we cannot bend the bars at site nowadays or at this time. But we already when we design any project with FRP bars, we already attached with the project the shop drawings for all dimensions of bent bars, and we can be reduce it easily at the factory. But in the site, we cannot bend the bars, especially for a small radius. But we can, I can add something for tunnel segments as an example. We can use the curvilinear GFRP bars without, and we can bend it easily. But when you speak with uh, close bend or very or 90-degree bend for GFRP bars, we cannot do it inside. But
As
for
long as, yeah,
large diameter, we can do it easily.
that's true. So in terms of the cost comparison, right, as I said, it depends on application to application. However, at certain times, especially in structural purposes, it might be just the material price might be expensive. However, if you take the total cost of project, which includes logistics, labor, installation, cost of material, at that time, it does become competitive, or I would say one can do an apple to apple comparison, or in cases which are non-structural, definitely there is a saving because of the quicker installation and lower cost of logistics.
But I need to add something, Rajesh. Okay, if we need to speak about the cost, we cannot speak about the initial cost. I know that for the initial cost, GFRP parts can be comparative or a little bit higher than steel. But if we speak about the long surface life, we speaking about repairs, deterioration of steel bars. All of this processing need a lot and additional money. So if we need to compare between the cost of GFRP bars and steel bars, we cannot compare for the initial cost. You need to compare between all the cost. It can be seems as I mentioned, it can be seem that the FRP bars a little bit higher than steel bars, but for the long term with the repair and you know that sometimes for repair process it can be costly as or higher than the initial cost.
Yeah, of course, with FRP, obviously one also need to remember that the design life or the longevity of the structure is much larger. So if a
Yes.
structure probably needs to be replaced every 20 years, whereas with GFRP, it will probably sustain more than that. So
Yeah.
obviously, yeah.
Especially if we speak about the applications in for infrastructure projects like tunnels, like any water sections, like any elements in harsh environmental conditions. You know that these elements prone to erosion and distortion for and damage quickly rather than the projects in harsh environmental condition.
Anywhere, anywhere where you need to protect the steel bar for corrosion. Let's say you're building a parking garage. In a parking garage, usually, typically, you spend lots of money trying to protect the steel bars. All that protection goes away. You don't need it when you replace it by the FRP bar. Therefore, your project will automatically be less costly from the start.
Ahmed, one question that has come up, and it's an interesting one. How does the epoxy fixing into concrete for GRP compared to steel reinforcement?
I need to add something in this, especially in this point. We have, as you presented, we have two types of resin, epoxy or vinyl ester. For structural elements or structural applications, we used vinyl ester resin because all GFRP codes mentions the vinyl ester is the most appropriate reason for a structural applications. For non-structural applications, we can use epoxy or vinyl ester. All of this reason easier epoxy or vinyl ester is combined with fiber during the producing of FRP bars. So once we have GFRP bars with suitable surface, it can be like steel bars. You don't see any epoxy or resin because it already combined with the fiber as one material for GFRP bars.
Perfect. I think there I think we've come to the end of our time with this presentation. If there are any questions, feel free to email us and we will try to answer them as soon as possible. Thank you so much. This is the first of the series of presentations and tech talks on rebars that we plan to do. So looking forward to having you guys again, probably in some time very soon. Thank you, everyone. Have a good day.
Thank you, Rajneesh.
Thank you, Rajneesh.